everybody, and welcome to a competitive programming video. If you don't know, I'm Sid, and I'm a high school senior, and I make videos on programming, productivity, and machine learning. If you're interested in knowing more about those topics, make sure to subscribe and follow me on Instagram and Twitter. My socials are in the description below. So let's get straight into it. Today's video is about graph theory, and basic graph theory concepts that should be useful for any competitive programmer and hopefully programmers in general. When you hear the word graph, the first thing you think about is probably line graphs, bar charts such as the ones over here. However, that's not what this video is about. Rather, we're going to be talking about graphs in the discrete math definition of the term, a collection of nodes and edges, as you can see in this very well drawn diagram. Like I just mentioned, a graph is a collection of nodes and edges. Essentially, they're a way to represent connections in between points of data. A lot of data sets can be represented in this way, and visualizing these discrete graphs gives you insight into a lot of different classes of problems. In the competitive programming sense and world, these usually boil down to looking at paths in between points, finding the shortest paths, and looking at minimum spanning trees. All things you'll understand the gist of fairly shortly. In computer science as a field, graphs have a much wider application. They're used to represent everything from knowledge, finite state machines, the structure of neural networks, and anything that is a discrete structure. If you don't know, discrete structures, of which integers are an example, have distinct separated values. Now that we have that definition out of the way, we can start looking closely at graphs so that you have a base off of which to build your knowledge of graph algorithms. This is the first in a series of videos on graph algorithms, and I'll be pumping out some animated content soon that'll go over some of the important graph algorithms like breadth first search, depth first search, Dijkstra's algorithms, Kruskal's, and Prim's. So if you're interested in those, comment and make sure to subscribe so you're up to date. Also, you can join my Discord to be notified when those videos go live. So let's get into discussing some graph terminology. When dealing with graphs, you'll come across a lot of terminology that you need to know, and I'll try to walk you through that terminology in the remainder of the video. Keep in mind that this is most definitely a crash course and not at all very deep or thorough, and if you want to learn more, I encourage you to do your own research, and there's plenty of long, lengthy courses that go into the details of graph theory, and graph theory is a very interesting subject, so I encourage you to go through that. But if you're just looking for a quick definition of terms, let's get straight into that. There are two main classes of graphs that you're going to be dealing with in competitive programming: directed graphs and undirected graph. An undirected graph is a graph where the edges have no direction. And you can travel along both directions of the edge. For instance, you can travel from this node to this node and then back to this node again. But like there's an undirected graph, there's also a directed graph. And you might be able to guess that directed graphs have directions to their edges, and you can only travel along those directions. So if you start at this node here, you can go from this node to this node, but you cannot go back to this node again, because this edge does not go in that direction. It only goes from node 0 to node 1. But you can go from node 1 to node 2, but now you're stuck. You can't go back from node 2 to node 1 or to node 0. So you'll notice these types of problems a lot. You'll notice these two graphs a lot, and these two types of graphs a lot. And competitive programming problems will have different versions will either have an undirected or directed graph based on what the problem is asking you to do. And if you want to know more about that, I'll have videos coming out soon. So let's quickly go over some other terminology that you'll see being talked about in problems and algorithm explanations. You'll often hear about something called a path. And a path is a sequence of edges that join a sequence of distinct or unique vertices. So let's quickly look at this example of a path. We go from node 0 to 1 to 2. This is a path, right? 0 to 1 to 2, that's a path because you have a group of sequence of edges that are connecting a sequence of distinct or unique vertices. distinct and unique mean the same thing in this context. Another term that you'll hear quite a lot is cycles. And a cycle is a group of vertices that are linked together in a closed chain. An example of a cycle looks like so. This is a cycle of length 3, and as you can see, it's cyclical in nature. You can go from here to here to here to here to here, and then just keep going, but you can't break into the cycle from anywhere else. Another common term you'll hear a lot is that of a connected graph. A connected graph is a graph where each pair of vertices has a path in between them. Simply put, it's a graph where you can go from one vertex to any other vertex. This cycle of line 3 here is also a connected graph. A type of graph that you'll see all the time is a tree. And a tree is what is known as a tree is an acyclic graph. It's a connected graph that is acyclic in nature. So you can go from any one node to any other node, but this contains no cycle, and each node has a degree of 2. And you're maybe asking yourself, well, what the heck is a degree? Basically, a degree, the degree of a node just tells you how many other nodes the node is adjacent to. So in this case, each node has a degree of 2 because, well, not each node. This node has a degree of 1 because it's only adjacent. Node 1 is adjacent to node 0 and only node 0, so this has a degree of 1. Node 0 is adjacent to node 1 and 2, so it has a degree of 2, so on and so forth. That's also a very, knowing the degrees of certain nodes also helps you when you're dealing with graph problems. So there are two main ways that you can represent graphs using code, and I won't detail into the code, but I'll give you a sort of pseudocode way that you can represent graphs. A very common way to do it, and this is what's usually taught first in a lot of graph theory courses, is that of the adjacency matrix. So assume we have this cycle graph here, right? Node 0, node 1, node 2. So we have a cycle of length 3, and you want to represent this somehow. We can use what's called an adjacency matrix, which are matrices that look like normal matrices. Right? And the element in the ith row and the jth column represents the number of edges from the ith node in the graph to the jth node in the graph. So the number of edges from node 0 to node 0 is 0, but from node 0 to 1 is 1, and from node 0 to 2 is also 1. The edges from 1 to 0, 1. The edges from 1 to 1, 0. The edges from 1 to 2, 1. The edges from 2 to 0, 1. The edges from 2 to 1, 1. And the edges from 2 to 2, 0. So this is an adjacency matrix, and it's a very common way of representing graphs, and it's something that you should definitely get down pat in your memory. The second way you can represent graphs with code is by using adjacency lists. And an adjacency list is a list of lists where a list at index I contains the vertices that are adjacent to vertex I. So let's take a look at what an adjacency list really looks like. So adjacency list, so the adjacency list index 0 would be equal to a list of 1, 2. Adjacency list at index 1 would be equal to 0, 2. And adjacency list 2 would be equal to 0, 1. Obviously, as you deal with larger and larger graphs, you won't be able to just completely write these things out by hand, and you'll have to represent them programmatically. But I'll cross that bridge in some of my code explanation videos, which will be coming out soon. And if you're really interested in knowing them, then there's hundreds of tutorials written on implementing a graph with code, and I encourage you to go and read them and implement them by yourself. There's also a few terms that I've left out of this video because I don't want this video to end up being uh, 30 to 40 minutes long. I'd rather keep it nice and short so that you can understand the gist of a lot of things quickly and then go do deeper research somewhere else, and so that this can be something I use to point to people when I make my algorithm videos in the future on graph algorithms. If you're interested in those algorithm videos, leave a like, subscribe, follow me on my socials, which are linked below, and join my Discord server if you want to keep up to date on new videos and blog posts that come out. Subscribe to my newsletter, which is also linked down below, for programming news, productivity tips, and just cool things that I see every week. It'll come out on Sundays, starting from now, and yeah, I hope you guys enjoyed the video. Go do some graph theory.